This is a short tutorial on the hydraulic principles behind the operation of the Thirsty Duck TDP series floating outlet and skimmer. The Thirsty Duck TDP series floating outlet and skimmer is a simple yet reliable flow regulator for use in stormwater detention systems and other gravity flow control applications. It can best be thought of as a floating weir or orifice, and it produces a nearly constant discharge rate as water surfaces both rise and fall. The Thirsty Duck TDP series floating outlet and skimmer is used for relatively low flow rate applications and comes in two sizes. Model TDP 184 produces flow rates up to 0.33 CFS, and model TDP 248 produces flow rates up to 1.8 CFS. Both models have a maximum vertical rise of 8 feet. The TDP series floating outlet and skimmer can be installed in open ponds or tanks. However, it is more commonly installed inside a precast concrete structure, manhole or vault, as pictured here. So, let's take a look at how it works. The heart of the TDP series floating outlet and skimmer is its flow restrictor module, which is both an orifice and an air plenum. The flow restrictor module is suspended from a float at a fixed distance below the water surface by 4 threaded rods. The threaded rods allow the flow restrictor module to be moved up or down to create the desired operating head. Vent tubes, which extend above the water surface, are connected to the flow restrictor module and allow air pressure to equalize below the orifice, creating a free discharge condition. As water passes through the flow restrictor module, it is conveyed to the outlet through an expanding tube called a bellows, which is specially reinforced with stainless steel rings to resist collapse from hydrostatic pressure. A skimming body surrounds the float and flow restrictor module and prevents floating oils, greases and other debris from passing through to the outlet. When the Thirsty Duck isn't floating, it rests on its nest. The nest stores the bellows when it is compressed, and it also serves as the outlet connecting flange. Thirsty Duck connects to the outlet with a standard ANSI pipe flange connection. Unlike traditional weirs and orifices which produce increasing flow rates with increasing water levels and decreasing flow rates with decreasing water levels, the Thirsty Duck TDP series floating outlet and skimmer produces nearly constant flow because it operates at nearly constant head. Depending on the depth of water over Thirsty Duck's flow restrictor module, it functions as either a weir or an orifice. Therefore, the design engineer only needs to understand the Weir equation and the orifice equation to calculate the flow rate Thirsty Duck will produce. When water flows over the flow restrictor module at very shallow depths, Thirsty Duck functions as a weir. At greater depths, it functions as an orifice. The depth at which weir flow transitions to orifice flow is known as the transition head. The transition head can be determined by setting the Weir equation equal to the orifice equation and solving for h. The Weir equation is used when the water depth is less than the transition head, while the orifice equation is used when the water depth is greater than the transition head. This chart shows the transition head depth for each of the Thirsty Duck's available orifice diameters. Note the transition head depth increases with increasing orifice diameter. Both the Weir and orifice equations contain the term C, which represents the coefficient of discharge. A value of 3.2 should be used for Weir flow calculations for models TDP 184 and TDP 248. While a value of 0.55 should be used for orifice flow calculations for model TDP 184. For model TDP 248, a value of 0.62 should be used for orifice flow calculations. These coefficients have been verified through a variety of laboratory trials and experiments and corroborate well with many published textbook values. A rating curve illustrates the relationship between water surface elevation, or stage, and flow rate. The Thirsty Duck TDP series floating outlet and skimmer has a unique rating curve for each of its available orifice diameters and corresponding ranges of operating head. The rating curve shown here is for a 4-inch diameter orifice at a design operating head of 8 inches. In order to illustrate the hydraulic advantage Thirsty Duck has over traditional static weirs and orifices, the rating curves for a weir and orifice, which produce the equivalent flow rate as the Thirsty Duck when its bellows are fully extended, have also been plotted. In general, the more separation there is between the Thirsty Duck rating curve and the equivalent weir or orifice rating curve, the greater the hydraulic advantage. Throughout this tutorial, the phrase nearly constant instead of constant has been used when referring to flow rate and operating head. Note the Thirsty Duck rating curve is not a perfectly horizontal line after the operating head has been achieved. This is because forces develop in the bellows which cause the Thirsty Duck to float slightly lower in the water as it rises. As each convolution of the bellows is raised from its resting position, the float carries additional weight and the total amount of weight is increasing linearly. After all of the convolutions have been raised from the rest, or compressed position, the bellows stretches much like a rubber band, creating tension, which increases exponentially as the bellows is stretched further. Since the total downward force acting on the float is increasing as Thirsty Duck rises, it naturally floats a little lower in the water. This in turn means the depth of water, or head, over the flow restrictor is increasing, resulting in a slowly but steadily increasing flow rate. This chart illustrates the general relationship between the downward force exerted on the float as Thirsty Duck's bellows is extended. The relationship between extension, weight and tension have all been determined empirically in the laboratory. The engineers at Thirsty Duck have developed a very useful spreadsheet tool, which can be accessed from the Thirsty Duck website. The tool generates the unique rating curve associated with each of the available orifice diameters and their corresponding ranges of operating head. The spreadsheet tool automatically selects the appropriate flow regime, weir or orifice, and accurately calculates the flow rate, while accounting for the slight increase in operating head which results from the forces developed in the bellows as the Thirsty Duck rises. The spreadsheet also makes consideration for free discharge and submerged outlet conditions. When the system water level is controlled by Thirsty Duck, we refer to it as a Case A installation. The diagrams on the screen illustrate typical Case A installations. Conversely, when the water level is controlled by a weir or orifice, we call it a Case B installation. The diagrams on the screen illustrate typical Case B installations. Case B installations are very useful for minimising the amount of system storage used to achieve Thirsty Duck's design flow rate. In a typical Case B installation, Thirsty Duck's flow restrictor is located behind and below the level of the control device. The diagrams on the screen illustrate how a Case B installation minimises the amount of the volume used compared to a Case A installation. Thank you for watching this short tutorial on the hydraulic principles behind the Thirsty Duck TDP series floating outlet and skimmer. If you have any questions or comments regarding this tutorial, please feel free to contact us through our website at www.thirsty-duck.com. We are always happy to provide technical assistance with designs and modelling at no charge.